Hello students, I am Dr. Kalyani S Kakad, Assistant Professor, Department of Pharmacognosy at Progressive Education Society, Modern College of Pharmacy, Nigri, Pune. In this session, discussion on modern extraction methods. The use of plant-derived medicinal dates back many centuries, although it is still under estimation in modern medicine. Plants remain the most important source of natural drugs. More than 30% of prescription drugs are natural products. More than 60% of anti-cancer and anti-infective drugs are natural products. The main sources of the drugs are as follows. Natural substances are obtained from plant microorganisms and animals. Some are semi-synthetic substances. These are the drugs that are manufactured by partial synthesis. Synthetic substances are the drugs which are manufactured by total synthesis. To carry out the phytochemical screening, the following point must be fulfilled. The first step, selection of promising plant material. Proper collection of selected plant, authentication of plant material, drying of plant material, grinding, cleaning, packaging and storage and preservation, extraction and fractionation of constituents, method of separation and purification, and identification of isolated compound by using a various analytical techniques such as structure elucidation by UV, IR, mass and NMR. Extraction and fractionation of constituents. There is no general universal method for the extraction of the plant material. The precise mode of extraction depends on the texture of plant material, the water content of plant material, the type of substances to be extracted or nature of the active constituents. Extraction, it is a process or in which the separation of medicinally active portion of plant or animal tissues through the use of selective solvent and suitable method extraction. The principal method of extraction are maceration, percolation, infusion, decoction, digestion, liquid-liquid extraction, distillation, Soxhlet extraction or continuous hot extraction. All these are the conventional extraction methods are used for a separation of medicinally active portion of a plant by using a selective solvent. Nowadays, modern methods or advanced methods are used for the separation of active constituent such as supercritical fluid extraction, microwave extraction, and ultrasonication. All these are some techniques recently used for extraction purpose. Here is the discussion on continuous hot extraction, also known as Soxhlet extraction process. Factors affecting the choice of extraction process. The choice of the process to be used for the extraction of a drug depends on the number of factors, such as the nature of a drug. It's very important. To check the nature. Suppose it is hard in nature, tough. So at that time, the percolation is the more suitable method. The crude drugs, it is in soft in nature. So maceration is the most suitable method. Stability of a crude drug, solvent, time duration, cost of the crude drug, and the recovery of the solvent. These are the important factors are considered for the choice of an extraction process. So already we have discussed. Again, the extraction may be defined as a treatment of the plant or animal tissue with solvent, whereby the medicinally active constituents are dissolved and most of the inert matter remains undissolved. The solvent used for extraction is known as menstruum, and the inert insoluble material that remain after mass extraction is called myrrh. Fundamental of mass transfer. Extraction, it is an example of a mass transfer process. So what is meant by mass transfer? Mass transfer is the net movement of a mass from one location to the another. Mass transfer occurs in the many processes such as absorption, evaporation, adsorption, drying, precipitation, membrane filtration, and distillation. Mass transfer is used by different scientific disciplines for different processes and mechanisms. A group of unit operation for separating the compound of mixture is based on the transfer of material from one homogeneous phase to another. The driving force for transfer is concentration difference or concentration gradient. Much like a temperature difference or a temperature gradient provides the driving force for heat transfer. This method covered by the term mass transfer operation includes such technique as indicated below, such as the distillation, liquid extraction. So, the Soxhlet extractor is a laboratory apparatus invented in 1879 by Franz von Soxhlet scientists. It was originally designed for the extraction of active constituents from a solid material. Typically, a Soxhlet extraction is only required where the desired compound has a limited solubility in the solvent and the impurity is insoluble in that solvent. So, these are some terminologies we use during the extraction process. Menstrual means solvent used for extraction. Macerate means solution of soluble constraint. Mark means residue left after the extraction. Here is a glassware set-down of Soxhlet apparatus. Soxhlet assembly contains the three important glasswares. The first is a round water flask. Second, thimble with a side tube and siphon tube, and condenser with a water inlet and water outlet. So the procedure of Soxhlet extraction, it is a continuous extraction of components from a solid mixture. Boiling solvent vapor rises up through the larger side arm and condensed drop of a solvent fall into the porous cup, dissolving out the desired components from a solid mixture. When the smaller side arm fills to overflowing, it initiates a siphoning action. The solvent containing the dissolved component is siphoned into the boiler below, and the residual solvent then drained out of the porous cup as a fresh solvent drop continues to fall into the porous cup. What are the advantages of Soxhlet extraction? Repeatedly bringing the solvent into contact with the solid matrix, maintaining relatively high extraction temperature with heat from a distillation flask, no filtration of extract is required. What are the disadvantages of Soxhlet extraction? Agitation is not possible in case of the Soxhlet device. The possibility of thermal decomposition of the target compounds cannot be ignored as the extraction usually occurs at the boiling point of the solvent for a long time. Conclusion: using a Soxhlet extraction is the way to separate the soluble material such as secondary metabolites from a powder of a fluid. A Soxhlet extractor repeatedly extracts with free solvent until it is stopped. Thus, it is possible to extract all the soluble material if given enough time. So, next session is on supercritical fluid extraction method. Supercritical fluid extraction, the use of supercritical fluid for the extraction of a range of materials, including plant products of medicinal, flavoring, and cosmetic interest. Supercritical state. Supercritical fluid extraction is the process of separating one component, such as active components or analyte, from another from a crude drug using supercritical fluid as the extracting solvent. Above a certain temperature and pressure, single substances do not condense or evaporate but exist as a fluid. Under this condition, the gas or liquid phase have the same density and no division exists between the two phases. So, CO2 at specific temperature and pressure get converted into the supercritical fluid, and that fluid is used as a solvent, as a fluid for extraction purpose. Principle of a SFE: a fluid have a density of a liquid and the viscosity of the gas. The supercritical fluid diffuses well through a solid and it is a good solvent for extraction purpose. Why the carbon dioxide is used as a source? Carbon dioxide is the gas of choice, and the reason for this becomes clear when considering its advantages. It is a natural product, chemically inert, non-flammable, perfectly non-toxic, easy to eliminate completely, readily available and inexpensive. That's why mostly the carbon dioxide is used as a choice for a conversion purpose. This is a supercritical phase diagram, how the CO2 at specific temperature and pressure is get converted into the fluid. Here is the x-axis temperature, note the temperature, and the y-axis pressure. Suppose at specific temperature and the pressure that CO2 is behaved as a fluid. Okay, so here is a critical point at the 31 degrees Celsius and 73 atmospheric pressure. CO2 is above this particular temperature and pressure. CO2 is converted into the fluid. Okay, so this point is known as a critical point. Once that critical point get reaches, CO2 is get converted into the supercritical fluid. So, phase conversion of CO2 is possible by monitoring, by changing the temperature as well as the pressure. So, here is a discussion on physical states of the carbon dioxide, which depends on pressure and temperature, deserve particular attention. At atmospheric pressure, CO2 is in gaseous phase. At temperature between minus 56.6 and 51.1 degrees Celsius and pressure of at least 5.2 bar, CO2 can exist in liquid form. Liquid CO2 cannot exist at atmospheric pressure. At temperature below minus 56.6 degrees Celsius, CO2 can occur in a solid state. All three physical states are possible only at the critical point. At the 56.6 degrees Celsius, and this one is the pressure. World-class technology for the natural products. There is a tremendous demand for a high purity and residual solvent-free extract of a natural product. Also, there is an increasing requirement of eco-friendly manufacturing process for the extraction of natural products. Supercritical fluid extraction technology provides an economical solution to provide a safe and eco-friendly way for extraction of natural products. Its superiority over the conventional technologies of extraction, especially for natural products in the food and pharmaceutical industry, is well recognized. Supercritical fluid is used in a textile for dyeing purpose, is an emerging innovative waterless technology for dyeing of textile fabrics that will revive the textile industries. Here is the discussion on what is meant by critical point. So the critical point marks the end of the vapor-liquid coexistence curve. A fluid is termed supercritical when the temperature and pressures are higher than the corresponding critical values. Above the critical temperature, there is no phase transition in that the fluid cannot undergo a transition to a liquid phase, regardless of applied pressure. A supercritical fluid is characterized by physical and thermal properties that are between those of the pure liquid and gas. The fluid density is a strong function of temperature and pressure. The diffusivity of a SF supercritical fluid is much higher than for a liquid, and supercritical fluid readily permeate porous and fibrous solids. So, supercritical fluid can offer good catalytic activity. In order to design and develop an supercritical fluid extraction process for medicinally active products with CO2, we need to know and optimize the solubility of the substance of interest, chemical class of moiety, and the extraction profile. Very important note is mentioned here. Here, during the process to improve the property of supercritical fluid CO2, some various co-solvents and modifiers are added during the process. So CO2 alone is not as selective as a good and pure solvent. CO2 capacity and selectivity may be improved by using an organic solvent, also called the co-solvent. Ethanol, methanol, with the function of modifying chemical interaction between CO2 and the substance to be dissolved in. But by doing this, the supercritical fluid extraction process becomes more complicated, with an extra chemical component need to be introduced into the process. However, the co-solvents can be easily separated from the product downstream due to the high selectivity displayed by the supercritical CO2 in this. So basic requirement in terms of the equipments are to measure the extraction profile, a small pilot scale apparatus can be used. Extractor and separator volumes do not need to exceed 1 liter each. So first, CO2 storage tank, a cooler to prevent CO2 from evaporating in the pump, a heat exchanger to control the temperature of CO2 entering the extractor, an extraction vessel, a heat exchanger to control the CO2 plus solute mixture entering the separator, and a separation vessel. These are the important basic components of a supercritical fluid extractor. Here is the schematic diagram. CO2 tank, cooling chamber, pressure adjustment, preheater coils, extraction cell are covered by a oven means to monitor the temperature here, and the sample collection folder. Here is a pilot scale supercritical fluid extractor is available in the various research laboratory. This is a schematic diagram and shows the various important steps of a supercritical extraction process. The first is the CO2 storage tank. In a tank, it is in liquid phase. Second step, CO2 passes into the cold exchanger to maintain its liquid state before entering into the high pressure pump. High pressure pump. Then the fourth, reheating. The temperature is raised up to the 31 degrees Celsius. So CO2 is supercritical. Once it is become a fluid in nature, then this fluid is passed through this extracting vessels. Okay. After extraction, the pressure and temperature, lowering the pressure and thus return of the CO2 a gas state allows the separation of the extract from CO2. Reheating, the temperature is maintained at 51 degrees Celsius. So separation, in the first separation stage, separation of CO2 from the extract by the gravity. Under cooling, the extract is decompressed gradually to be underdrawn into total safety, and by cyclonic separation in a second stage separation, separation of CO2 exactly by a centrifugal force. So at the end, still in a gas state, CO2 is cooled for a liquefaction, and again it is back into the CO2 tank. So here is a schematic diagram of a supercritical extraction process. First stage, second, third, fourth, fifth, and then 6, 7, 8, 9, 10, and finally 11, and again recovery of the CO2 back into the container. So these are the steps, explanation of all these 11 steps. Those are shown in this particular schematic diagram with explanation. So process description for a commercial scale plant. The raw material in powder form is filled to an extractor. The liquid carbon dioxide from a CO2 tank is pre-cooled by passing it through the pre-cooler. This pre-cooled liquid carbon dioxide is then pressurized by means of a positive displacement of a plunger pump to a pressure above the critical pressure of CO2, that is 73.8 bar. High pressure liquid CO2 is then heated above the critical temperature of CO2, that is 51 degrees Celsius, by passing it through preheater. CO2, which is now in a supercritical state, enters the extractor in which the raw material is loaded. The supercritical fluid dissolves the substances on the basis of solubility depending on operating condition. The supercritical fluid with soluble extract enter the separator where the pressure and temperature are reduced sequentially so that solubility decreases and the extract precipitates in the separator. Finally, the clean CO2 without any traces is recycled back to the CO2 tank via condenser. So these are the advantages of a selection of CO2 as a solvent. Carbon dioxide is generally regarded as a safe for a food product. It is inexpensive and easily available. It is non-toxic and non-flammable and inert to most material. These are the advantages of supercritical fluid extraction method. Extract with delicacy and freshness close to the natural. High pure earth, high potency of active components get extracted and have a shows longer shelf life extract. This method is eco-friendly and green technology with no residual solvent and effluents. This method having a high flexibility of process condition. It is possible to perform simultaneous fractionation of extracts. High yield compared to the solvent extracted products. In this method, low batch time for extraction is required and recycling of CO2 is possible and low operating cost is required. The disadvantage, high capital investment for equipment. Supercritical fluid technology requires sensitive process control, which is a challenge. In addition, the phase behavior of a mixture of solute and the solvent has to be measured or predicted quite accurately. Generally, the phase behavior in a critical region is rather difficult to control. Our recent research has provided much more insight into this phase behavior. These are some examples uh, by the supercritical extraction of some medicinal aromatic plants. Here is essential oil is extracted from eucalyptus species by using the supercritical fluid extraction method. This paper was published in 1999. The title was Isolation of Eucalyptus Oil by Supercritical Fluid Extraction. The second example, flavonoid glycosides, flavonoids and terpenoids are isolated from Ginkgo biloba. This paper was published in 2002. The title was Extraction of Pharmaceutical Components from Ginkgo biloba leaves using supercritical carbon dioxide. Third example, essential oil extracted from mentha species. This paper was published in 2001. Title of paper, Extraction and Isolation of Salvia and Mentha spicata insularis essential oil by supercritical fluid extraction. Oleoresins are extracted from Piper nigra. This paper was published in 1999. So all these are the examples of the various components, secondary metabolites are extracted by using a supercritical fluid extraction method. Mostly the examples are essential oil, oleoresins, and flavonoid glycosides and terpenoids. So commercial application of supercritical fluid extraction. Extraction of natural products such as spice oil and oleoresins, flavors, fragrances, and colors. Decaffeination of tea and coffee. Production of uniform and ultrafine particles. Supercritical fluid used in textile dyeing of fabrics. Supercritical fluid cleaning of high precision metals, components, and drying of aerosols. These are some other commercial applications of supercritical fluid extraction method. Thank you, everyone.